Today my topic is automorphism. Let G be a group and an isomorphism from G onto itself is called an automorphism of G. Okay, that means phi G to G, this isomorphism is called automorphism. For example, so number 1, identity mapping IG from G to G. This is an automorphism. Okay. Again, number 2, suppose G is an abelian group, then phi G to G is defined by phi of A equal to A inverse is called, this is an automorphism, because phi of A compose B equal to equal to AB whole inverse equal to B inverse composition A inverse equal to A inverse composition B inverse equal to phi A composition phi B. So phi is a homomorphism. Also we can check that phi is an bijective mapping. So this is phi is an isomorphism, and this isomorphism is called automorphism. Okay, again there is a trivial example also. G equal to number 3, G equal to complex number C plus the mapping is phi G to G is defined by phi of Z equal to Z bar. You can check this is also an automorphism. Okay, the set of all automorphisms is denoted by odd G. Okay, the set of all automorphisms of G is denoted by odd G. Okay, and we can verify that this automorphism of G is forms a group under mapping composition. Okay, because for example alpha and beta belongs to automorphism of G. So that means alpha is a mapping from G to G, beta also mapping from G to G. Okay, both are, since automorphism, so they are both bijective mapping. So their composition alpha beta also bijective mapping. Okay, since alpha and beta are isomorphism, then their composition also an isomorphism. So this is alpha and beta are automorphism. So alpha composition beta is belongs to auto of G. Okay, again number 2, composition of mapping, compositions of mapping is associative. Okay, number 3, IG identity automorphism is an identity element. Number 4, since alpha is G to G is an isomorphism, that means inverse mapping also G to G is an isomorphism. So therefore alpha inverse also the automorphism. Okay, so that's mean auto G with respect to mapping composition forms a group. But this is not abelian group in general, because alpha composition beta may not be equal to beta composition alpha. So this automorphism of G with respect to mapping composition forms a non-commutative group in general. Again, automorphism of a group G in particular the permutation of the set G. So automorphism of G is a subgroup of SG. Automorphism G is a subgroup of permutation group of G. The theorem is, let G be a group and the mapping alpha G to G is defined by alpha x equal to x inverse for x belongs to G, then alpha is an automorphism if and only if G is abelian. Okay. One part is obvious. If G is abelian, then alpha x equal to x inverse is an automorphism. But if this is an automorphism, so let alpha G to G is defined by alpha x equal to x inverse is an automorphism. So then alpha of xy equal to alpha x alpha y. So this is implies xy whole inverse equal to x inverse y inverse, and this is implies xy equal to x inverse y inverse whole inverse, this is equal to yx for all xy belongs to G. So this is implies G is an abelian group. Now we have an important proposition. Let H be a normal subgroup of the group G. Then G acts by conjugation on H as automorphism of H. That is, more precisely, the action of G on H by conjugation is defined by H goes to G inverse. For each G belongs to G and H belongs to H. Okay. So for each G belongs to G, conjugation by G is an automorphism of A's. Okay, that is, let H be a normal subgroup of the group G, then G acts by conjugation on H as the automorphism of H. That is, H goes to G, H, G, but this is a conjugation. For each G belongs to D, the conjugation by G is an automorphism. G, H, G inverse means the H is conjugate by H. Conjugate by G. Let phi G of H equal to G, H, G inverse for each H belongs to H. That is, actually phi G is conjugation by H, by G. Phi G is conjugation by G, and G normalizes H. G normalizes H because H is a normal subgroup of G. So G, H, G in G, H, G inverse belongs to H. So that means this phi G is a mapping from G into itself. From H into G is maps H into itself. That means phi G is a mapping from this mapping is from H to H. Also, we know that conjugation defines an action. Okay. Now, phi of E of H equal to E H E inverse. That means equal to H equal to IH. E is the identity element of G, and this is identity mapping from H to H. And phi A composition phi B equal to phi of AB, because for all AB belongs to G, because phi A composition phi B of X equal to phi B of X. This is equal to phi A BX B inverse, and this is equal to ABX AB whole inverse. So phi of A compose B equal to phi A compose phi B equal to phi of AB. Again, phi G is injective and surjective mapping. Since G inverse H1 G belongs to H, such that phi G inverse H1 G equal to H1. So for H1 belongs to H, it has a preimage G inverse H1 G. So phi G is a bijective mapping. Okay, and phi G inverse is the inverse of phi G. Is the inverse of phi G. Okay. So phi G is the bijective mapping. Again, again phi g h k equal to g h k g inverse. So this implies g h g inverse g k g inverse, and this is implied g h g inverse and g k g inverse. So this is implies phi g of h, phi g of k. So therefore phi g is a automorphism of h. Therefore the conjugation by any fixed element of G defines an automorphism of H. Okay, so that means phi G belongs to auto of H. Okay, so therefore the conclusion is the action of G on H by the conjugation is defined for each G belongs to G, and H goes to, that means H goes to G H G inverse, that means conjugation by a fixed element is an automorphism. Okay, again by previous Cauchy's theorem, so permutation representation psi G2 SH defined by psi G equal to phi G. So this is actually left action of G on H. Okay, so it has an image contained in the subgroup automorphism of H. Okay, this is actually Cauchy's theorem. Now car psi equal to G belongs to G, psi G equal to IG, that means identity mapping, and this is equal to identity automorphism psi G equal to, and this is equal to all G belongs to G such that G H G inverse equal to IG equal to H. So this is equal to actually centralizer of H. By isomorphism theorem, G quotient car psi, that means CG of H is isomorphic to SH. Okay, by isomorphism theorem, G quotient car psi, the car psi one is CG of H is isomorphic to SH. Okay, so that means the permutation representation afforded by this action phi G is a homomorphism G into automorphism H with kernel CG of H. Okay, in particular CG of H, G quotient CGH is isomorphic to the subgroup of automorphism of H, as automorphism of H. Okay.